Hello grade 12s and welcome to this video on the photoelectric effect. In this video we're going to be working through the theory on the photoelectric effect. So if you're interested in working through problems with me, please be sure to watch the videos that follow. In grade 10 you would have worked through, or your teacher would have explained to you what the electromagnetic spectrum is. And you would have found out that the electromagnetic spectrum is made up of radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Furthermore, you would have found out that radio waves have a very high wavelength, but their frequency is low. Gamma rays, on the other hand, have very small wavelengths, but their frequencies are high. From this, you would have drawn the conclusion that as the frequency increases, the wavelength decreases, and vice versa. When we take frequency and multiply it by wavelength of some electromagnetic radiation, we find that it gives us the speed of light. And when this light is traveling through a vacuum, then the speed of the light is equal to 3 times 10 to the power of 8 meters per second, described by the symbol c. This constant will be given to you in your table of constants on your formula sheet. In grade 10, you focused on the wave nature of light. We basically said that light is made up of electric fields, moving electric fields that generate moving magnetic fields. And based on this, we have that the waves are able to move through a vacuum. We would have also said that electromagnetic waves can be described as transverse waves. Now in grade 12, we move away from this and we start to describe the particle nature of light. So light or electromagnetic waves can be described as waves or particles. When describing light or electromagnetic waves as particles, we say that it is made up of packets of energy called photons, and that each of these photons carry a specific amount of energy given the symbol E, that we can calculate by saying Planck's constant multiplied by the frequency of that specific electromagnetic wave. Planck's constant will be given to you on your formula sheet in your table of constants. So if you struggle to memorize it, please always just refer to your formula sheet. Using this formula, we can conclude that as the frequency increases, the energy of the waves increase. And it is for this reason that gamma rays, which have the highest frequency, are the most dangerous to humans. They have a high amount of energy which allows them to penetrate through our bodies and cause damage. On the other hand, your radio waves, which have low frequencies, have very low amounts of energy. And that is why we allow them to travel all around us, and we say that there are no known dangers of these radio waves. They're not able to penetrate through us. We are going to focus specifically or focus on visible light in more depth in this section. We say that visible light is actually white light, and it can be broken up into a spectrum of colors. But to classify the spectrum, we speak of the 7 colors: red, orange, yellow, green, blue, indigo, and violet. In summary, we say Roy, G, Biv. In the spectrum, our red light has the smallest amount of energy because it has the longest wavelength and the smallest frequency. Violet light, on the other hand, has a high amount of energy because it has a very high frequency relative to the red light. Remember, we are only focusing on this small part of the electromagnetic spectrum. Visible light, which is the light that our eyes can detect and allows us to see things. Remember, if an object appears to be green, or if you are looking at my screen and you see the red writing that I am using, the red pen that I'm using, the reason why it appears red is, well, in this case, no, I'm using the wrong example. Let's go back to something that is green. Let's say that you are looking at a leaf. Okay, the leaf appears green because it is absorbing all of the white light, the red, orange, yellow, blue, indigo, and violet, but it is reflecting green light. Okay, so visible light, this is light that our eyes can detect, and everything you see around you is as a result of visible light being reflected off of objects. Now, this section, of course, is about the photoelectric effect, which I've already said describes the particle nature of light. We say that the photoelectric effect is the process whereby electrons are ejected from a metal surface when light of a suitable frequency or suitable energy is incident or shines on the surface. So guys, when you have a metal and you shine light that has enough energy or high enough frequency on this metal, what it actually does is it causes the electrons from the metal to jump out of the metal. So one of the devices that we use to ensure that the photoelectric effect actually does happen, or to detect the photoelectric effect, is a photocell. What we do is we connect a photocell, this big object at the top, it's obviously been enlarged. We connect a photocell in a circuit that contains an ammeter. The ammeter is there to detect current, of course, and cells. If our circuit is complete, then of course we will find a reading on the ammeter. But notice our photocell contains an anode and a cathode that are separated by air. There's just air in between them. Or actually, sorry, it's not air. They are in a vacuum. So since they're in a vacuum, it means there's no air, no particles, nothing of that sort to complete the circuit. This electrode, the anode, will be connected to that side of the circuit, and this one to the other side. So what basically happens is we shine light that has a high enough frequency on our cathode. When we do that, we find that the electrons are able to jump out of the metal. So this is made up of a metal. So the electrons are able to jump out of the metal, and they can therefore enter the anode and complete the circuit. That is basically what is happening over here. Except I do think it might be happening in the wrong direction, because if you look at this, which is from a past paper, you will see we have exactly the same setup. We have our battery or cell, we have an ammeter, we have light that is shining on one of the electrodes. Basically what is happening here, so I prefer this image, what is happening is electrons will move provided that the circuit is complete. Once they get to this point, they are now in the vacuum that is shown by the circle. And they need to move to this side. But in order to move, well, they can't just move. They're not just going to build up and therefore move. So what we do is we shine light on this metal, and in doing so, the electrons jump out onto the other electrode, and the circuit is complete. That is how a photoelectric cell, or also known as a photocell, works. It works upon this principle called the photoelectric effect. Now, I've described to you already that energy of light can be calculated by saying Planck's constant multiplied by the frequency of the light. But since C is equal to the frequency multiplied by the wavelength, we can solve for the wavelength by saying frequency is equal to C divided by the wavelength, substitute it in there, and then say energy is equal to Planck's constant multiplied by C divided by lambda. These are two forms of exactly the same equation. In grade 10, you may have learned about quantum theory. And what quantum theory basically says is that when you have light, right, your photons cannot be broken up into parts. They contain specific amounts of energy, and that is why we refer to them as photons or quanta. What this basically means is that when you take light and you shine it, so remember these are packets of energy that are traveling to the electrons. these packets of energy will either be completely absorbed or they will not be absorbed at all. Because you either take a whole packet or you take nothing. That's basically how this system works. And that is what's being described over here. What is important in all of this writing that you see is that a photon must have a certain minimum amount of energy to overcome the force of attraction between the metal and the electron, and of course to remove the electron from the surface. Now guys, this minimum amount of energy is referred to as the work function, and it is given the symbol W subscript 0. You need to have the specific amount of energy called the work function in order for these electrons to be emitted. This or something higher. Now in the previous diagram, you would have seen the word monochromatic light. I'd like to refer to lasers to explain what monochromatic light is. The word mono refers to one. And basically, monochromatic light is light of a specific frequency. It is red, or it is green, or it is blue, or it is orange, or it is that color, magenta, or whatever in between different colors, beige. It's right in between something. It's a specific type of color, but it's only that color. That is what monochromatic light means. If you see the word coherent, it just means that they travel like this instead of being scattered like that. So a laser has coherent light, but if we look at an LED light, or if we look at the light bulb in your room, that is incoherent light because it travels in different directions. And guys, it's for this reason, the fact that laser light is coherent light and directional, that it is actually very dangerous to shine it in your eyes. Now let's speak more about the work function. We've already described it as the minimum energy that an electron needs in order to be freed from the metal. Notice that each metal has a specific unique work function, so specific to that material. Sodium, for example, has a work function of 2,28. But if we go on to magnesium, which is a metal, it has a work function of 3,68. Going to platinum, it has a work function of 6,35. That tells us that platinum, the electrons in platinum, require more energy to be released from the metal than the electrons in sodium. That's basically what we are saying. Sometimes you will see that the work function, instead of being given to you in joules, which is the SI unit for work and energy, they will be given to you in EV. EV stands for electron volts, and 1 electron volt is equal to 1,6 times 10 to the negative 19 joules. You might remember just this number over here. This number corresponds with the charge on an electron. So if you are looking for this number, just go and look for your charge on your electron, but you basically just take any of these numbers given in EV, multiply them by that to get your answer in joules. Now, if you find that Planck's constant multiplied by the frequency gives you an energy that is smaller than the work function, what is going to happen is that the photon will not have enough energy to emit an electron. And because of that, it will it can be excited to a higher energy level, but will quickly fall back to the original level, and it will emit energy of the same frequency. That is what makes metal shine. But the focus here is basically on the fact that if the energy of the light is smaller than the work function, then the electron will not be emitted. If the energy, so Planck's constant multiplied by the frequency, is equal to the work function, then the photon will give the electron the exact amount of energy that it needs to be emitted from the metal. So the electron will be emitted. Sometimes, however, you're going to find that the energy is higher than the work function. In a case like this, the energy, so the work function amount of energy, will be used to emit the electron, so it will be emitted. but any extra amount of energy. So when you take this total energy and subtract the work function, that extra energy, very, very important, will be converted into kinetic energy. What is kinetic energy? It's energy of motion. As a result, we say that the energy of the photon, the energy of the light, will be equal to the work function plus kinetic energy. If we find that this value is bigger than that value, then of course we're going to have kinetic energy. Expanding these equations, we say that energy is equal to Planck's constant multiplied by frequency. We have the work function. In a moment, you're going to find that the work function is equal to Planck's constant multiplied by the threshold frequency. I'll explain that in a second. Ek will be equal to half mv squared, where m is the mass of one electron, because these are electrons that are being emitted. So, back to this threshold frequency. The work function is actually a measure of energy. The threshold frequency, if the work function is the minimum amount of energy needed to emit an electron, then the threshold frequency is the minimum frequency of light needed to emit an electron from a metal surface. So they are related to each other. The one is just frequency, the other is energy. But they are both the minimum amount of their quantity needed to emit an electron. Of course, you know that frequency is related to wavelength. So sometimes instead of talking about frequency, we may speak about the cutoff wavelength. The cutoff wavelength is related to this threshold frequency, which we can also call the cutoff frequency, by the formula C equals F times lambda. We solve for lambda and we get C over frequency. So if ever they give you the cutoff wavelength, remember you can calculate the frequency using this equation, which is basically one form of this equation that is given to you on your formula sheet. Except on your formula sheet, if I'm not mistaken, they often, yes, they do. If you look at your formula sheet, instead of giving the symbol C, they use the symbol V. Because V is for speed. Whether we are in a vacuum or we are moving through water or we're moving through glass, the formula V equals F times lambda will always work. All you need to do is substitute in a C and make sure to use the constant value, which is 3 times 10 to the power of 8 meters per second. So I've placed in here your formula sheet, or the section of your formula sheet relevant to the section. You may remember the word period that is related to frequency. Just take note of that because it might be useful to you if they want to throw in period into these problems. Here we have the formula for energy, which is H times F. And if we want to use the wavelength, then we use E equals H times C over lambda. They've included two forms of the photoelectric effect equation. We tend to use this one where we use E subscript K. Right? Where E subscript K max is the maximum amount of kinetic energy that your electron will have if your photon has more energy than the work function. They show you here at the bottom that work function is calculated by saying Planck's constant multiplied by the cutoff or threshold frequency. And they say kinetic energy is equal to half mv squared. So all of your formulas are here in one form or another. Take note of this so that you know how to use these formulas later. Sometimes you may want to calculate the kinetic energy that your electrons are going to have. Okay, so you want to find out what is the relationship between the kinetic energy of the electrons and the energy that we give, the energy that we provide. In order to find the kinetic energy from our photoelectric effect equation, we simply solved. So here they solved for Ek. we can use values of EK and frequency in order to draw a graph, like the one that we find over here. Now notice on our x-axis we have frequency. On the y-axis we have kinetic energy. This is the y-axis. So, and we have a straight line. That means that we can describe this graph with a line, the standard equation for a straight line, which is y equals mx plus c. Our y value is the kinetic energy, where the x value is the frequency. That means that the c value, using this equation, we see that the c value, remember c is for your y-intercept. If you take your graph and you extrapolate it so that it cuts through the y-axis, the value that you get there is the negative of your work function. Take note of that, that's very important. And if you calculate the gradient, you are going to find Planck's constant. Take note of this. It's very, very, very important because they love to give graphs. So just to recap, if you're given a graph of this sort with frequency that's the frequency of the light, frequency of the photons on the x-axis, and on the y-axis you have EK, the kinetic energy of the electrons. The gradient gives you Planck's constant, and the y-intercept gives you the negative of the work function. So if you want the work function, you're going to have to divide by negative or multiply by negative to get the opposite of that value. So it would be a positive value. All right. This is, I think, the last equation. Sorry, not equation. The last PowerPoint in the set of PowerPoints. No, I lie. There's one more. Sorry, guys. You guys can read through this. It basically summarizes everything that I've said. You can also read through the application. It's going to help you. But of course, you know, the best method is always to list what you have, sub it in, and go from there to what you would like to calculate. It is true in a lot of cases you're going to start off with the frequency, and from there you can get the energy of the light. They might give you the cut-off frequency. From there you can get the work function, or they might give you the wavelength, and from there you can use or get the work function. And using these, you can then go to your photoelectric equation. Okay, but you guys can read through that. I'm not going to waste time on that in this video. This last slide, grade 12s, is very important because a lot of learners mess up in this section. There is a difference between increasing the frequency of the light and increasing what we call the intensity. When you have a light and you increase its frequency, what it basically means is that you are changing the color. So in this picture on the left hand side, we have a change in frequency. We have 3 waves in all 3 pictures, 3 waves coming in. The first is a pinkish red color. I'm going to call it red for now. Then we have this green, and then we have blue. What you need to remember is blue light has a higher frequency than red light. Therefore, blue light has a higher energy than red light. When we say that we are changing the frequency of the light, it means that we are literally just changing the color and energy of the light. That is what frequency is. On the other hand, intensity is about how bright the light shines. So here we have less intense light, and here we have bright light, which has a high intensity. Same color. Yes, this one might appear on the left a bit more yellow. It appears a bit more yellow because of the light bulb itself, the actual glass. But in terms of intensity, we have a low intensity here and a high intensity on the right hand side. In the picture on the left, all of the intensities are the same. If I would like to increase the intensity of this red light, I will shine, okay, it needs to be more coherent perhaps, but I will go and I will shine just more light. I will make it more bright. That is what intensity is about. Now, this is what you need to understand. It is very, very, very important. By increasing the frequency of the light, you increase the total energy. Remember, the energy of your photon will equal to the work function plus the kinetic energy of the electron. When the energy is in excess, higher than the work function, we end up with kinetic energy. So when you increase the frequency, this is H times F, if you increase the frequency, you increase the energy, and you therefore increase the kinetic energy of the electrons. That is what you are changing. They can move faster. The speed of them increases, right? So the rate at which charge flows is going to increase. That's what's going to happen, because when you have a change in charge over a smaller or greater amount of time, then the current is going to increase. All right. That is when we change, or in this case, increase the frequency. Now, sometimes you may increase the frequency of the light. So let's say, for example, we have an electron. And this electron needs light of green frequency or higher. Okay. But you go and you shine red light on this electron. Okay. You can go and you can increase the intensity of the red light, and still nothing's going to happen. No electrons going to be emitted, and there will be no kinetic energy, because if nothing's emitted, there's no kinetic energy. Okay. What I need you guys to understand is that frequency specifically is going to change the kinetic energy. On the other hand, when we change the the intensity, what we are basically doing is we are releasing more packets of energy, okay, at a time. So there we are changing, sorry guys, I went off track for a moment, right? So what we are doing is, when we do that, you're going to find when there's a greater intensity, if we have green light, so these electrons require green light, and we are shining on green light, but we increase its intensity, what will basically happen is that more electrons will be emitted. In other words, there will be more charge emitted. It will not change the kinetic energy of these electrons. They will still move at the same speed. Very, very important. Because in this case, when we change the intensity, we don't change this value. We're only changing how much packets we are releasing. Okay. So since there are more packets, if these packets have enough energy, we're going to find that the current will also increase, because we are increasing that. But nothing will happen to the kinetic energy. So they love to talk about this in multiple choice sections, or it will be the very last question that they bring up in problems on the photoelectric effect. If we have enough frequency, enough energy, then in both cases the current will increase. But when we move or change the frequency, the kinetic energy will increase or decrease. When we change the intensity, nothing at all will happen to the kinetic energy. That is what I need you guys to understand here. We've reached the end of this theory video. This is basically all of the theory on the photoelectric effect. So if you've made it so far, guys, I'm really proud of you. Thank you for watching this video. Remember that in the next videos, I will be going through the examples. Thank you so much for watching.